During a colorful ceremony on July 30th, 1952, the Chesapeake Bay Bridge, which for decades had been a dream in men's minds, was formally opened to traffic. This graceful steel structure, more than 4 miles long, spans the bay about 5 miles north of Annapolis, between Kent Island on the east and Sandy Point on the west. Built as a highway connection to join western Maryland with its eastern shore, it also serves as a link in the north-south express routes bypassing the metropolitan centers of Baltimore and the District of Columbia. The opening of the bridge to traffic marked the passing of the familiar ferries, which formerly plied between both shores. Along with the bridge came intrastate route changes that were planned to shift the flow of traffic and speed the traveler on his way. The bridge was designed by the J.E. Greiner Company of Baltimore for the Maryland State Roads Commission. The entire 30,000 tons of steel in the superstructure were fabricated and erected by Bethlehem Steel Company. One of the longest overwater steel structures in the world, the bridge is outstanding for the many different types of spans incorporated in its design. The roadway rises from the western shore on beam and girder spans. These are followed by a series of 10 simple deck truss spans which form the curve in the bridge. As the elevation increases, 3 longer and heavier deck cantilever truss spans connect with a 2,900 22-foot suspension bridge across the main shipping channel en route to Baltimore. Extending shoreward are more deck cantilever units, a through truss cantilever over the secondary ship channel, then girder and beam spans. An earth-filled causeway extending 1,700 feet in shallow water marked the beginning of construction at the east side of the bay. On the west, the pier locations show the curve that the bridge must have in order to cross the ship channels at right angles and terminate at selected points on both shores. From survey platforms paralleling the bridge line, engineers pinpointed the locations of the deepwater piers to signal the start of underwater construction. Most of the deepwater piers were built in the following manner. In a dredged area of the bay bottom, timber piles were driven to support the bottom form, or bearing mat. When this form was sunk and accurately positioned by the guides, which extended above water, steel bearing piles were inserted in marked openings. The piles were driven deep into the bay bottom, leaving 10 feet of length projecting above the mat to be embedded in the concrete shaft. Then, on this base, prefabricated steel caisson sections were lowered into position and connected by divers. When the caisson, with its built-in reinforcing steel, was filled with concrete and properly cured, the pier was completed. The wooden bottom form for each pier caisson was designed with openings to accommodate the steel bearing piles. The openings in the platform were marked with raised numerals so that divers could guide each pile into its proper place. A guide tower erected temporarily in the center of the bottom form served as a survey target during the sinking operation. At the same time, the steel caissons that form the pier shells were being fabricated at Bethlehem's Baltimore Ship Repair Yard. These shells consisted of 2 or 4 tapered bell-bottom legs, joined by steel plates. Wooden templates were used in pre-assembling the caissons to ensure a perfect fit when the sections were joined at the bridge site. Each caisson section was fabricated on a separate barge for transport to its pier location. In the sinking operation, the bell-shaped bottom section was first lowered onto the wooden form. The middle sections were then submerged and bolted together. After the top section was lowered and secured, concrete was poured underwater into the bottom form. Once this had set, the permanent steel piling supported the pier and its load. The caisson was then filled with concrete and the pier top formed above water. As the pier work progressed, 3 of Bethlehem's fabricating shops in Pennsylvania, Pottstown, Rankin, and Bethlehem, began delivery of the steel to storage yards in Baltimore. Here it was classified and stockpiled until needed. Meanwhile, out on the bay, approximately a mile from the western shore, a specially designed tower derrick boat constructed a temporary erection dock alongside the bridge line. Various units of the bridge structure were assembled on this deepwater dock so that they could be floated into position conveniently. In the erection plan for the bridge, these large girders were used as part of the falsework upon which the simple deck truss spans were constructed. Using the tower derrick boat, the first of these truss spans was assembled 145 feet above the water. At the same time, erection of the beam spans progressed outward from both shores. From steel plants to the fabricating shops to the storage yards, a steady supply of steel moved to the bridge site. Workmen next installed bearing shoes for the 100-foot girders that follow the shorter beams in the bridge structure. These girders, located several hundred feet from shore, were lifted into position by the tower derrick boat. With the erection of beam and girder spans, the long-awaited overwater stretch of steel was well underway. On January 9th, 1951, the first truss span was completely assembled at the erection dock, ready to be floated to its piers about 70 feet away. All later floating operations followed a similar pattern. 2 pairs of steel barges having watertight flooding compartments were built by Bethlehem for these floating operations. They were equipped with pumps to regulate buoyancy, winch engines and anchor lines to provide maneuverability. When partially flooded with water, the barges were moved under the falsework girders by means of the winches and anchor lines. Ballast water, indicated by float gauges projecting through the barge deck, was then pumped out. As buoyancy increased, the barges rose and the entire assembly was lifted off the dock. With the steel span afloat on the barges, the deck engines pulled on lines attached to anchors sunk in the bay bottom, moving the floating assembly over into position. And when the span was over its piers, the barges were flooded slowly and the span settled on its permanent supports. The falsework was then floated out and placed back on the erection dock in a reverse operation. The long girder spans were also floated using a single pair of barges. These spans, 200 feet in length, were assembled across gaps in the bridge left for that purpose. The heavy plate girders for each span were shipped in sections of 50 and 100 feet. At the bridge site, they were spliced, braced, and riveted into a complete unit, weighing about 250 tons. For the floating operation, a false-worked frame on a pair of barges was moved into the gap beneath the span. As in truss flotations, the span was lifted from its supports by pumping water out of the barges. It was then floated into position and lowered onto its piers. Back at the erection dock, 2 derricks had been mounted on the first floated span to erect the steel for the remaining truss spans. As each 350-ton span was completed, it was floated on the barges and hauled away from the erection dock. It was then moved by tugs to a point alongside its final location in the bridge. When lines from the barges were connected to anchors, the tugs backed away and the deck engines maneuvered the span between its piers. Of the 10 simple deck truss spans in the western approach, 4 were 250 feet in length and 6 measured 300 feet. After each span was secured on its piers, the false work was returned to the erection dock and rebuilt. Careful checking was required to ensure the proper elevation for the next floating-in operation. The last simple deck truss span closed the gap in the western approach, extending the steel work continuously 1 mile from shore and completing the curve in the bridge. When this floating operation was finished, the erection dock was extended to accommodate the larger deck cantilever spans. Meanwhile, construction of the suspension bridge began with the preparation of the surfaces of the main tower piers. The bearing areas were ground to a perfectly level plane under the watchful eyes of a field engineer. The tower sections, which had been stockpiled in a Baltimore harbor yard, were cleaned and given a field coat of paint. As they were scheduled for delivery, the sections were loaded onto barges and towed the 20 miles to the bridge site. Erection activity was now concentrated at the West Tower Pier with the arrival of the tower base sections. Dry cement was spread over the pier tops to provide a smooth bearing surface and to serve as a seal against moisture. Slowly, the first tower section is swung from the barge to its pier and carefully lowered over the anchor bolts. Using the derrick boat to lift the steel into place, the west side tower then began to take shape. The tower sections were fabricated as 5-cell units between 20 and 30 feet in length. Light, movable platforms bolted to the tower provided safe working space for the raising gang. Diagonal bracing ties the sections together and joins the tower legs into a single unit. Inspection ladders built in each tower cell enabled workmen to climb from one level to the next. With perfect coordination between men on the derrick and those on the tower, the sections were guided between the splice plates. When aligned and on signal, they were lowered into place, then pinned and bolted securely. The first 6 tiers of tower steel were erected by the derrick boat, which was capable of lifting the 30-ton sections 174 feet above the bay. When the west tower reached this height, Chicago booms were mounted on the tower to erect the remainder of the steel. Having completed its job on the west tower, the derrick boat proceeded to erect the first 6 tiers of the east main tower. Using the derrick boat and later the Chicago booms, this steel was erected by the same procedure used in raising the first tower. Signals were carried by microphone to loudspeakers located at the working level and in the hoisting engine room on the pier below. While the derrick boat erected the side towers, both main towers were rising steadily skyward. They reached an elevation 354 feet above the surface of the bay when the topmost sections were bolted fast. The towers were then crowned with grooved saddle castings to support the main suspension cables. Securing the last of these saddle castings left only the field riveting to complete the towers. From heater to catcher, rivets flew through the air to the tune of riveting hammers. As the riveting gangs moved upwards on the tower, the first of the deck cantilever spans neared completion on the erection dock. For this span, the girders that had served as false work for the smaller units were replaced by a 360-foot truss span, which later became part of the bridge. Erection and flotation of these heavier structures followed the same pattern used for the earlier floating-in operations. The first 480-foot truss span is ferried across the bay from the dock to its final location near the center of the bridge. The braced tower supports the far end of the span and gives it stability. A rocker bent on the near end permits slight movement caused by changes in temperature. Keyways in the steel bearing plates prevent the sidewise shifting of the span. At journey's end, barge lines were secured to anchors so that the winches on the barges could pull the span between its piers. Final adjustments in the alignment of the structure were made as the heavy span settled slowly onto its supports. A lot depended on split-second timing and close teamwork. After the span was secured, the false work was floated out and again returned to the erection dock. Here, as at all other locations where men worked over water, safety boats patrolled ceaselessly. Up on the structure itself, supervisors and all personnel met once each week during working hours to discuss safe working practices. Demonstrations and safety measures added interest to these meetings. Men were shown the proper use of firefighting equipment, how to wear hard hats for the greatest protection, how to do every job the safest possible way. The sequence of erection of the deck cantilever spans east of the suspension bridge consisted of floating alternate 480-foot anchor spans into place, then bridging the 600-foot gaps between them by extending steelwork out from each end of the floated spans. The tower derrick boat erected the cantilevered steel about halfway across the opening, while a small derrick moved eastward to close the gap and complete the span. By that time, the next anchor span had been floated onto its piers, and the cantilevering process was repeated. This combination of floating and cantilevering was also used in erecting the through cantilever structure. The two side spans were assembled at the erection dock and floated into place to serve as anchor units. The through cantilever type of construction was used to give maximum vertical clearance over the secondary ship channel without having to increase the height of the adjacent deck-type spans. When the anchor spans were in place, the derrick boat erected the 780-foot center span between them. The steel framework was extended first from one side, then the other, until it was joined at the center by the closing members. At this point, the deck span adjoining the through cantilever portion of the bridge remains to be erected. Part of this span was assembled on a car float in Baltimore, towed directly to the bridge site and hoisted into place. A combination of lifting beams and wire rope falls was used in making this lift. Hoisting engines installed up on the bridge deck raised the 400-ton span into its final position. The vertical hangers on the previously erected steelwork were pulled back during this lifting operation. With the connection pins driven, these hangers support the west end of the span. The east end was bolted to the rocker bent on which it rests. The bridge now stretched unbroken for about 2 miles from the eastern shore. The two highest anchor spans were next floated into place at opposite ends of the forthcoming suspension bridge. Bethlehem's erection superintendent literally talked the 950-ton span into position on its piers. Next, the corresponding span on the west side of the suspension bridge was floated in and a cantilever arm extended westward. The last truss span to be assembled at the erection dock was then maneuvered into the opening using breast lines connected to the piers, as well as anchor lines and tugs. Movement of the assembly was so slow that it was scarcely noticeable. One end of the span rests on a rocker bent, and the other is supported by the cantilever arm. When the floating structure was aligned, the vertical hangers were lowered and connected to the span with heavy forged pins. These pins permit longitudinal movement during changes in load and temperature. When this connection was made, the western end of the span was lowered onto its rocker bent. This flotation virtually completed the steelwork from both shores to the suspension bridge area, where construction of the cables was now underway. 2 temporary footbridges had already been strung across the tower tops from anchorage to anchorage to provide working space for the men during this operation. Instead of stringing individual wires to form the main cables, prefabricated twisted strands were used for the Chesapeake Bay Bridge. Each strand came pre-stressed or stretched to a predetermined length. By means of an endless tramway hauling system, the strands were pulled eastward across the tower tops from one anchorage to the other. Workmen accompanied the strands in the 4,000-foot journey to keep them from fouling or twisting in transit. The strands were pulled across one at a time, with a strand for one cable being followed by a matching strand for the other. The socketed ends of all strands were locked in position in the anchorage plates. Steel shims were later used to bring the strands into final adjustment. At the tower tops, the strands were lifted from the temporary roller path and placed in the cable saddles. At night, when the temperature was most uniform and there was little wind, the layer of strands placed that day was adjusted to the proper sag. Every strand was marked for its final resting position in the saddle. Also, every one was numbered for the space it was to occupy in each main cable, shown here in cross-section. Thus, the 55 main strands and the 6 smaller ones making up each cable were compacted to a diameter of about 14 inches. Each cable was brought to its final form with the insertion of aluminum filler strips along the outside strands. Then wire was wound around each cable to a point where it entered the splay castings. The cables were held fast by clamps at the anchorages and at the side tower saddles, but held only by friction on top of the main towers. Ironworkers next attached cable bands for the wire rope suspenders, which in turn support the roadway steel. When these were in place, erection of the suspended roadway started at the towers. Sections of the roadway were assembled on barges at Baltimore, towed to the bridge site, and lifted into place. These sections, which weighed from 50 to 125 tons apiece, were supported on lifting beams during the hoisting operations. Four sets of wire rope falls were temporarily clamped to the main cables directly above the section being raised. The lead lines ran along the cables to the tower and down to the hoisting engines on the pier below. When the suspender sockets were secured in their brackets, the hoisting lines were slacked. The bridge section now hangs from the suspenders. The lifts were made in a carefully planned sequence to maintain a reasonably uniform distribution of load on the 2 main cables. As many as 4 completely assembled sections were lifted into place in a day's time. Finally, the closing section of the suspended structure was hoisted into place near the west tower. 190 feet above the surface of the bay, workmen casually slipped the last suspender sockets into place just 1 year from the start of erection of the suspension bridge. From below, these simple structural elements form an impressive pattern as they are repeated one after the other. And from above, the diagonal bracing members of the suspension span are equally impressive as they recede in the distance. The span flanking the west side of the suspension bridge had already been erected by this time. The remaining gap east of the suspension bridge was shortened by a cantilever arm extending over the anchorage pier. The structure that had previously served as part of the falsework for the heavy flotations was used to close this last opening in the bridge. Signaling the spanning of the Chesapeake with steel, supervisory personnel, workmen and guests participated in a traditional flag-raising ceremony just before this closing span was lifted into place. The 400-ton unit made its ascent approximately 21 months from the day Bethlehem started the erection of this 4-mile-long superstructure. The steel now stretches from shore to shore. The roadway was already in various stages of completion. The suspension bridge floor system was finished by a small derrick that rolled along the 2 lines of open steel roadway grading. Meanwhile, paving operations, which began soon after the first spans were erected, were keeping pace with the roadway steelwork. Paving forms were fastened to the roadway steel and overlaid by a double layer of reinforcing bars. More than 1,700 tons of reinforcing steel were used in the bridge deck alone. Concrete for the floor slab was transferred from mixer trucks to power dump carts and discharged in front of the paving gangs. After rough finishing, the slab was sprayed with a special curing compound. Precast sections of the concrete parapet were next installed on extensions of the floor slab. The heavy steel guardrail was then bolted in place. A 2-inch wearing surface of asphalt completed the paving. All over the bridge, finishing touches were applied in preparation for the opening. Suspension cables were rounded out with the aluminum filler strips, then heavily coated with a preservative paint and tightly wrapped with steel wire for protection against the weather. The cable was sheathed in wire between the bands and along the entire length of the backstays to the anchor piers. Finally, the wrapped cable was coated with aluminum paint. As the load on the cables increased with the addition of the concrete roadway slab, the bolts on the cable bands and saddle castings were carefully checked and adjusted for proper tension. The cable bands were then sealed with molten lead. The final coat of paint applied to the suspenders, the towers, and other steelwork protects the entire structure and adds to its rugged beauty. Awaiting dedication on July 30th, 1952, the Bay Bridge, an overwater highway to the motorist and landmark to the mariner, stands out in bold relief against the Maryland sky. As tuneful music replaced the staccato sound of the riveting hammers, state officials and guests, representatives of the designers and the builders of the bridge, gathered to participate in this historic event. Through television, the unseen audience witnessed, along with those present at the dedication exercises, Maryland's Governor T.R. McKeldin, assisted by former Governor W. Preston Lane, Jr., officially opening the bridge for service. And so, another Bethlehem-built bridge takes its place among the greatest structures ever conceived for the convenience of the travel-bent and the business-bound motorists. To that end, Maryland has, at last, united its eastern and western shores as steel spans the Chesapeake Bay.